and this. So the change of states of solid to liquid, let me put my arrow like this, from solid to liquid is known as melting. The change of state from liquid to solid is known as freezing. The change of state from solid to gas or gaseous state is known as sublimation. Whereas the change of state also from gas to solid is known as deposition. The change of state from liquid to gas is known as evaporation. Evaporation. The change of state from liquid to gas is known as condensation. So we're all familiar with all these terms except condensation and sublimation. So condensation is a process. Condensation is a process whereby vapor loses some of its energy, or let me say of its kinetic energy to a colder body and changes to a liquid state. And for sublimation is a process whereby gas changes to solid, without passing through the liquid state. So generally, we may assume that before a gaseous state can change to a liquid state, to a solid state, it will need to pass through the liquid state. Before gases can turn to a solid state, it will need to pass through the liquid state. But in the process of sublimation, it does not even need to pass through the liquid state before a gaseous substance can be changed or transformed to a solid substance. Brownian movement. This movement was observed by Brown. Mr. Brown is a botanist. He was able to deduce that particles are constantly in rapid motion. So Brownian movement is a theory. Okay, rapid motion. So under Brownian movements, we're also going to talk about two variables. We have diffusion and osmosis. Diffusion is the movement of particles through a medium from a region of higher concentration to a region of lower concentration. while osmosis is the movement of particles through a semi-permeable membrane from a region of lower concentration to a region of higher concentration. So diffusion is the movement of particles through a medium from a region of lower concentration to a region of from a region of lower concentration to a region of sorry. This is the movement of particles through a medium from a region of higher concentration to a region of lower concentration until they are evenly diffused. An example is when a perf, when you spray your perf, you see that the concentration at the beginning, when you first spray it, will be higher than the concentration when it has been diffused, when it has been evenly diffused around or all over the room. Maybe you're in a room now and you spray the perfume, it will be very effective from the beginning. Gradually, the effect will degrade until it is evenly diffused. Now, in the case of osmosis, this is the movement of particles through a semi-permeable membrane. That is, there's a medium, there's a semi-permeable membrane, and it moves from a region of lower concentration to a region of higher concentration. Now, an example is, let's say a yam, a tuber of yam. So you have a slice of that yam, and you know how yam is always okay. Let me just put this to illustrate. So yam has pores like this, and then so for liquids to be able to pass through this membrane in terms of osmosis, then it needs a medium. Then you need to add salt and the liquid. Now, this salt aids the movement of the solid particles. The salt aids the movement of solid particles, of the liquid particles, I mean, from a region of lower concentration to a region of higher concentration. So this is just a sketch of what osmosis and what diffusion is all about. So now we can move ahead to gas laws. Gas laws. So before we move into gas laws, let's talk about gas pressure. Gas pressure is the force per unit area exerted by a gas. So before we can talk about gas laws, we just need to understand what gas pressure is. And gas pressure is the force per unit area exerted by a gas. So we have different laws postulated by different scientists that talks about gas laws. So before we move to gas laws, let's talk about general kinetic theory of gases. Okay, sorry. Kinetic theory of gases. So the first one is that gas molecules are in rapid motion and collide with one another and with the wall of the container. That's for the first one. You have the other one. The collision of gas molecules are perfectly elastic. The third one is the forces of attraction of gas molecules are negligible. This brings us into gas laws. So we have different gas laws from different scientists, and the first one is Boyle's law. The first law we're going to dive into is Boyle's law by Mr. Boyle. Boyle's law. So Boyle's law states that Boyle's law states that the volume of a fixed mass of a gas is directly, provided temperature remains constant. So mathematically, the law states that the volume of a fixed mass of a gas is inversely proportional to its pressure, provided temperature remains constant. So when you're talking about gas laws generally, okay, let me just put this notes. Generally, experiments involving gas and its calculations requires four, okay, let me write it in words. Requires four variables, which are temperature, pressure, volume, and number of moles. But in Boyle's law, we're just going to make use of two variables, which is pressure and volume. Because from definition, it states that the volume of a fixed mass of gas is inversely proportional to its pressure, provided temperature remains constant. Mathematically, we have volume inversely proportional to pressure. K is constant. So therefore, we can also break it down. To remove this sign of proportionality, we're going to have this as K over P. This K is a constant. Okay, sorry, I mean to say temperature. T, which stands for temperature. So this K is a sign, is a constant of proportionality. So therefore, K becomes PV. So in the case of having more than a pressure and a volume, so where we have our volume and our pressure, or you have it like this, we have our volume and we have 1 over pressure. So this shows that directly proportional, inversely proportional. So the reason why I had to draw the two different diagrams is that in a case whereby you're not seeing this diagram, maybe you're used to this diagram already, you do not see this diagram, you may assume that this is not correct. So it's either you draw it like this, where we have our volume here, inversely proportional to the pressure, or you have it like this, our volume directly proportional to, now you can see I'm not putting just pressure, I'm putting it as 1 over P, which is equivalent to the same thing. So if I'm going to have this directly proportional, sign of proportionality for inversely, it was like this, inverse 1 over P, which is the real diagram. Then directly the value of this 1 over P. So you can see that this is equivalent to this. So if you're having your diagram like this, you can also have it like this. This also show that, so this is another diagram to show